Okay, so this is the lecture for day one of Math 263. So let me just go over some basic sort of concepts that we'll be looking at throughout the course, and basically what you've done before in your Math 261 course that we'll be doing. In your Math 261 course, Calculus 1, you looked over the derivative and the integral in one function of one variable. So let's recall first the concept of the derivative. So suppose you have some function y equal f of x, and you have some tangent line to the curve y equal f of x, which is the best linear approximation to this curve y equal f of x near the point x equal a. So what do I mean by that? Well, I mean that this curve here is this line here, this tangent line, is somehow some linear function, and it best approximates this function. It's as close as is possible. And we'll make these concepts more concrete. So if I look here, well, the derivative in calculus 1 was defined as, well, the slope of this tangent line. And so the derivative of y equal f of x at a was just the limit as h goes to 0 of the slope of the secant line through the point a. Well, that doesn't quite actually. I didn't actually go through that point, but through the point a f of. And so if I look here at my secant line, this here, through a f of a plus h, f of a plus h, then the slope of this secant line should approach the slope of your tangent line, if it exists, as h goes to 0 of, well, the slope of the secant line is just f of a plus h minus f of a over h. So, well, f of a plus h minus f of a, I'll just call that the change in f. So delta f sub a of h. And as h goes to 0, I should have the change in f over h should go to 0. Okay. I can rewrite that as follows. So instead of writing f prime at a, let's write d f sub a of h. Let's denote this by f prime at a times h. Okay. So then I get that the change in f, delta f of a at h, that this should equal, well, the change, the differential, d sub f sub a at h, what I've written here, times, well, plus, well, our error. And our error is little o of h, which just means that the difference between these two, when divided by h, should go to 0, which is basically what we've written here. Okay, so in this course, what we'll do is we will extend this to multiple dimensions. And so in multiple dimensions, it'll just be the change in f at a, where a here is now some sort of vector. It's some sort of multi-dimensional object. At h, I guess this is a vector also. at h will just be the differential of f at uh, sub a, this vector, at h plus this little o of h. And we'll try to somehow make sense of this. In the second part of the course, we'll be looking at the integral. And so, if you recall, the integral of some function, say y equal f of a, between a and b is just the area under this curve, assuming, well, it's a signed area under this curve. So it's just the integral from a to b of f of x. And so, by the fundamental theorem of calculus, we have that the integral from a to b of the derivative of f is just f evaluated at, well, the integral from a to b. And so at the endpoints a and b. And so we'll denote the endpoints of a and b by this little curly. So it's the curly d of the interval ab. So this notation here just says that f of x evaluated at curly d of this interval is just f of x evaluated at the endpoints a and b. And so that's the fundamental theorem of calculus. Now, the integral, I can write this statement as follows. It's just the integral over the interval a b of the differential d of f. And I'll just be equal to, so that's what we wrote here. Now, the integral, I can write the integral for this thing evaluated at the boundary. So I can just say, well, this notation, whatever it means that I'm just going to evaluate f at the endpoints. So this notation is, well, the integral over this curly ab, the interval of ab at f is just f of x evaluated at the endpoints a and b. So we will extend this fundamental, this is the fundamental theorem of calculus. We'll extend this fundamental theorem of calculus to multiple dimensions. And this will be called Stokes' theorem. And so, when it'll just be the integral over some region where I'm integrating over some form. So the exterior derivative of this form is equal to the integral over the boundary of this differential form. And that is sort of the culmination of our course, is when we'll be able to look at that and say that, oh yes, that's really a fundamental theorem of calculus written in multiple dimensions. And so it'll actually be Stokes' theorem, but also Green's theorem and the divergence theorem, all written up into this one sort of nicer form. Okay, so that's really it for the introduction.